Hi, everyone. I'm Lilian, Head of Analytics at IPercept, and today is session number 2 of our webinar series on CNC machine monitoring. In session 1, Carol walked you through why traditional vibration monitoring falls short on complex CNC machines. You know, the scalability problems and the baseline traps. If you missed it, the recording is available, and I recommend you watching it. What we're going to do today is go through the motion pattern method more in detail and describe how it actually works. So I think it's 12:01 now, so we can start. This is what we're going to cover today. We start with the test cycle. So how the machine generates its own diagnostic data. Then we read the pattern, what the healthy and degraded signatures actually show us. After this, we're going to describe the absolute severity assessment. So answering the questions on why no baseline and no waiting periods are required. In the fourth section, we're going to go through 5 different examples of real-life cases where this method influenced maintenance decisions. And finally, for closing, we're going to talk about the key takeaways and next steps after this session. The questions are more than welcome throughout the session. Please just write them at the chat, and I will address them at the end. Now, session 1 ended with a crucial question. How do we go from a motion measurement to a maintenance decision? And the answer is what we're going to cover today. The quote at the top is what makes this method fundamentally different from traditional vibration monitoring. It's not just something looks different from last week, but rather your x-axis is at an accelerated stage of degradation. The observation is related to a ball screw knot defect. This statement is actionable. It's something that you can use to make a decision. And today, we're going to follow the process that actually produces that statement, from the moment the test cycle is run to the signal patterns that it derives and how these are mapped to a specific defect in a component. And I hope that by the end of this session, this statement will make sense to you, not just as a claim, but mechanically and physically speaking. So, how does the machine generate diagnostic data in the first place? The answer is the test cycle. We run a predefined G-code sequence in a controlled, repeatable manner to generate a signature that we can analyze. The process has 4 steps. First, installation. The smart device is installed on a kinematic chain, and it only needs a 24-volt supply. So no connection to the controller, no IT project, no changes in the machine software. The installation is typically around 1 hour. After this, we have the test cycle. We run a predefined G-code sequence every week, which lasts about 5 minutes. The device is self-triggering, which means that it detects the test automatically, and the operator doesn't need to do anything special when it's running. Third is the analysis. The algorithms compare the data that is captured to a physics-based digital twin to identify deviations and map these to specific failure modes. And fourth is the planning. The output is a component-level health prediction and recommendation that you can then use to guide your maintenance decisions. Not just something is wrong, but which subsystem, which component, and what to do about it. If we go a bit deeper into the test cycle, we can see that it has 4 parts, and these parts are designed to excite every subsystem and critical component in a CNC machine. For terminology clarification, when I say subsystem, I mean a specific mechanical system in a CNC machine. CNC machines are comprised of 3 different types of subsystems. We have spindles, linear feed drives, and rotary feed drives. And as you can see in the slide, all of these are covered by the test cycle. So first, we have the spindle test. This runs each monitor spindle across different speeds, covering its working range. Then we have the circular test. This one engages 2 linear feed drives at the same time, making a circle and going through each of the planes. So X, Y, and then Y, Z, and X, Z, both clockwise and counterclockwise directions. After this, we run each of the axes isolated from each other in a linear test, which is basically going from the minimum to the maximum stroke a few times, one after the other. And finally, we have the rotaries test. which runs all rotary feed drives from a minimum to a maximum swivel range a few times. These machines are so inherently repeatable, we're talking about millisecond level precision, which means that any deviations from the signature actually tells us something specific about the mechanical configuration, or more specifically, degradation of these machines. So we've established now how the test cycle actually generates the data. But what does the data show? The answer is motion patterns. The key concept is that these patterns are fingerprints. Each component in these machines has its own characteristic signature, and degradation changes that signature in predictable, identifiable ways. If we think, for instance, of ball screws or bearings or gearboxes, they all have their own fingerprint, different frequency content, different amplitude profile. They do not mix on an unreadable blur, but rather they superimpose in ways that can later be separated. For instance, if we imagine a linear feed drive, we have the ball screw, the bearings, the coupling, and all of them can be engaged at the same time in the movement, but they have very different geometries, which means different signatures. These signatures will degrade differently over time and will also show in different ways in the data that is being collected. The next thing to know is that any kind of degradation changes the fingerprint predictably. Motion-dependent defects produce characteristic frequencies tied to the component's geometry. So if a bearing has a defect, for example, that frequency appears at the same specific orders every time the test runs, regardless of the speed. As work progresses, the amplitude rises or new symptoms may appear, such as harmonics or sidebands. On the other hand, localized defects like stick slip or a surface bit on a ball screw shaft create periodic impulses at the same position in the test cycle every time. All of these symptoms are mapped, understood, and then tracked by the system. This results in component specificity without ambiguity. Anomalies appear at the exact moment the subsystem is excited. If the linear test shows an anomalous peak at a position of 250 millimeters on the x-axis stroke, it is pointing to something specific at that position. Not the machine has a problem, but rather the machine has a problem here in this component at this point of the movement. This is a real example. We have two machines, same type, same test configuration. Left is healthy and right has a defect detected. What we're looking at here in the plots is time domain acceleration data. We have time in the x-axis and acceleration in the y. And on the left panel, we can see a healthy signature. We have the acceleration spikes, which are normal, expected from the linear test. They happen when the linear feed drive is traveling to one side and then reversing direction. So we have a reverse of direction here, and then a stroke, and then a reverse of direction again. Aside from these acceleration spikes, we don't see much. In between them, the RMS is low, and there are no unexpected patterns. On the right side, however, we have that the acceleration peaks are still there, but they are blurred in between everything else. What the system is picking up are actually consistent amplitude bursts at repeating intervals throughout the stroke. This is a very characteristic signature of a position-dependent defect. In practice, what it means is that when the linear feed drive is traveling from one side to the other, instead of having a smooth movement, is having outwards or small bumps throughout the stroke. So the key point at the bottom is the defect appears at the same predictable point in the test cycle every time. That's what separates a real defect from noise. Noise is random. It can be a nearby machine or a forklift driving by, but a defect instead is structural. It shows up in the same place at the same amplitude every single time. And that repeatability is what allows the system to track progression over time and know how fast this is degrading. So we've seen what the patterns can look like. Now, how do we turn a pattern deviation into a severity prediction? The challenge with most monitoring systems is that they compare today's signals to yesterday. So if the machine was already degraded when you install the system, you have no way of knowing that, and your baseline will be corrupted. However, the motion pattern method takes a fundamentally different approach. There are 3 steps in this method: capture, compare, and diagnose. First, we have capture. The device records the data from the test cycle, the full motion of it, and analyzes it. Then we have compare. These analyzed patterns are compared to the physics-based digital twin model of how the specific subsystem should behave when it's healthy. This reference is not learned from historical data. It is rather derived from the physics of these machines. How this happens is that there is a parameterization step where we establish the mechanical configuration of each of these subsystems. And this is what determines the expected signature. If we take a linear feed drive, for example, we indicate if this is belt-driven or directly coupled. That actually influences the expected signature. So the reference is always accurate to what the subsystem should produce when it's healthy, regardless of what condition it was in when we started the monitoring. And finally, we have diagnose. Deviations from this pattern reveal components that are degrading and how severely. The system doesn't just flag that something is different. It identifies the pattern and which failure mode is consistent with this pattern so that we can also know how far along the degradation curve it actually is. The contrast at the bottom is really what matters. Traditional monitoring is relative. You compare to yourself, even if you have a corrupted reference. However, the motion pattern method is absolute. The reference is always a healthy, known virtual machine, so it does not change based on the history. So, what does the absolute assessment actually produce? We have 4 stages for each subsystem mapped to the potential to functional curve, which show a subsystem life cycle and tells you how you need to act. First, we have the stable stage. Here, the subsystem is normal. There's wear within expected bounds, but there's nothing to do except continue monitoring. After this, we have the observable stage. We have early signs of wear that are detectable and the pattern can be traced, but it's not at a concerning scale. Here we can plan maintenance when it makes sense. Accelerated stage then is when the degradation is progressing. You're in the steep part of the curve, so this one, and any additional stress in the machine can be risky. It is worth scheduling the maintenance during the next window. And latest, we have the critical stage. This is very close to failure, and any additional load could cause a breakdown. Here, we recommend to act immediately. What the PF curve shows you is a picture of where you are in this subsystem life cycle. However, the stages add the context of what you need to do right now. The other thing we're noting here is that because the reference is physics-based, then the first measurements are already meaningful. The predictions only improve as more data is collected. This is actually those 4 stages, what they look like for a milling spindle. Real patterns from the 4 different stages of degradation. We are looking here at frequency domain data, frequency in orders in the x-axis, and amplitude in the y. First, we have the stable stage, where we have a clean, sparse spectrum. There are expected harmonics, and those are inherent to the spindle, but the noise floor is very low, and there's nothing in between them. Then we have the observable stage. Here are the first signs of change. Some additional frequency content, and the energy has redistributed. If you weren't actually comparing to a healthy reference, you might miss this stage. After this, we have the accelerated stage. The spectrum is significantly richer. There's higher noise floor, there's more peaks with higher amplitudes. The pattern structure has completely changed. This isn't just more of the same, it is substantially different. And lastly, we have the critical spectrum. Here we can see that the spectrum is very dense. There's a very high noise floor, and the harmonic structure is really breaking down. Here, the machine is clearly telling us that there is something wrong. As you can see from each stage, they look completely different from one to the other. They are just not slightly worse, but a different pattern altogether. And the key point to take from this is that the degradation is visible in these subsystems long before the failure. We're talking maybe weeks or months. So you do have time to act. You just need to be watching. So until now, we've covered the method end to end. Now we're going to look at real life cases. So cases where this motion pattern method actually changed the outcome of a maintenance decision. And when I say change the decision, I mean that it either would have, without the monitoring, we would have either a missed fault or a broader intervention that was not necessary. The specificity of the analysis is what made the better outcome really possible. So here we have a case A, a linear feed drive on a 5-axis milling machine. We have 4 different phases of this case and 4 different plots also that showcase each of these phases. In the plots, we have frequency domain spectrum of the linear test of the linear feed drive, and with frequency in hertz in the x-axis and amplitude on the y. I'm going to walk you through each of these phases because I think they really showcase the capabilities of the motion pattern method much better than a single detection event. So in the phase 1, we have the subsystem at an observable stage. There are certain drive side bearing frequencies that have appeared, which means that there's a defect identified in this component. The team was flagged and the maintenance team started to planning for an intervention. Then we have the phase 2. We now see that the free side bearing frequencies also come up in the spectrum. And more than that, we have a richer and higher noise flow throughout the entire spectrum. This is really a sign of a critical stage. The repair was scheduled and carried out immediately. However, now we have phase 3, and this is the one that I really want you to remember, because after the repair, everyone would have expected that the axis is at a brand new state. However, after the first test cycle, the system immediately flags improper belt tensioning. It turns out that a new fault was introduced during the repair itself. It was physically challenging for the technician to tension the belt properly, and the system flagged this immediately after the repair. This was, of course, communicated to the customer, and a follow-up repair was scheduled. In the phase 4 now, we have that the belt was retensioned properly and all the frequency contact is absent. The subsystem is confirmed stable and healthy. So without the post-monitoring here, that machine would have likely caused an unplanned stop from the belt drive defect. How long before that happened? We don't know, but we do know it did not happen. Now we have a case B. This is a spindle underperformance. And the story here actually starts after the repair, not before it. The spindle was replaced, a new unit was installed by the OEM, and the expectation was, of course, that the unit would behave perfectly, and it didn't. Here we are again looking at frequency domain data. We have frequency in the x-axis in orders and amplitude in the y. The left panel shows what the expected behavior was. So it should produce a clean, sparse spectrum with only the expected harmonics. The right panel shows what we got instead. Here we have much more frequency content throughout the spectrum, with also higher amplitudes and maybe a raised noise floor. Here it's clear that the pattern did not match the reference, and that was documented and flagged to the customer. This documentation is what really enabled the customer to start a conversation with the OEM, which eventually led to filing a warranty claim that was successful. But I think this case is more than just about the money. It's about having objective evidence. Without monitoring, the customer's options were to accept an underperforming spindle, likely without even noticing, or to file a subjective complaint. With the monitoring instead, the conversation was really aided by data and facts, which meant that all parties could come together and find a solution. The estimated savings for this case are around $100,000 and 315 hours of avoided downtime. Now we have KC, the rotary axis in the automotive industry. And this one is slightly different from the previous cases because the value here isn't in catching a failure, it's delaying a replacement. A bearing defect was identified during the early monitoring period. The system flagged it and the subsystem was in observable stage. However, it then started to degrade, and the customer didn't want to let it degrade further without doing something about it. The caveat here is that the replacement for the bearing had a very long link time, so the customer needed to act. What the system enabled was a targeted maintenance intervention, pre-tension adjustment of the bearing, and servo parameter optimization, which was guided by the system feedback. The customer was able to test different controller parameter configurations in this rotary axis and understand the effect of each of them. You can see here 3 different panels. What we're looking at is time domain data acceleration in time in the x-axis, acceleration in the y, and we also have 3 different measurement directions in each of the plots. The orange signal is the one that you want to look at because it's the one that shows the most activity. The first one has the suboptimal parameters, which the machine had been running on for a while. We see very high amplitude at the start and ends of each of the steps in this plot. Then we have the second panel, the tested parameters. This was a first improvement which adjusted a little bit better the machine's dynamics, but it was not the optimal state. Lastly, we have the optimized parameters on the right after the final tuning. These parameters brought down the amplitude levels to a better performance, which suited the best the machine dynamics. And this, together with the pre-tensioning of the bearing, improved the response of the subsystem further. As a result, the degradation trend stabilized and the component lifetimes was extended. This was enough to procure the replacement bearing, which had a lift time of 5 to 6 weeks, and schedule the planned maintenance. What was avoided then was downtime during these 5 to 6 weeks, which, as we all know, is a significant number in the automotive industry. We have 2 more cases here briefly. We have the coupling looseness. A defect in the linear feed drive was identified. The anomalous patterns clearly pointed to coupling looseness, not ball screw or guideway degradation. A targeted replacement was scheduled and it was carried out, restoring the subsystem to a stable stage. Without the monitoring, a general replace the axis recommendation would have likely been issued, and the ball screw and maybe the bearings would have been replaced. So the estimated savings here are 50 to 60,000 euros. And we have then the case E, which is the same defect, 2 different components. We have 2 machines in production, both showing similar position-dependent defect anomalies. If you looked at the symptom alone, you would see that maybe they could be treated as the same failure mode. But the component level analysis identified linear guide damage in one machine and ball screw shaft damage in the other machine. These are, of course, different root causes, which lead to different corrective actions. A generic replace the axis here would have led to at least 1 unnecessary replacement. So the estimated savings are 30 to 40,000 euros. The common thread is the system didn't just say something is wrong. It said which component and what to do about it. And that is the difference between a targeted intervention and a broad one. So we've arrived to the 5 takeaways. I'll go through them briefly, and this is what I want you to carry out from the motion pattern method. 1 is the test cycle is the precision diagnostic instrument. It uses the machine's own motion system to generate a controlled, repeatable signature. 2 is that the motion patterns are fingerprints. Each component has its own, and degradation changes them predictably. 3 is that the absolute severity means no waiting. The physics-based digital twin provides a prediction from the very first measurements, and the predictions just improve over time. 4 is that component level specificity matters. The system tells you which component, how severely, and how urgently it's degrading. That specificity is what enables targeted decisions instead of broad interventions. And 5 is that error propagation is all too real. When one component degrades, it can affect its neighbors in the kinematic chain. So monitoring one component in isolation is not enough. We have 3 more sessions coming up. Session 3 goes deeper into the subsystems and the failure mode analysis. So if you want the theory and engineering behind the defects we looked at today, that's the one for you. We have session 4 as well, which is the practical guide on how to implement this on your CNC fleet. And lastly, session 5, which covers operational monitoring. collision tracking, utilization, load intensity, and how process health really connects to OEE. So thank you very much for your attention.